Hey guys, welcome back. Now continuing in a deep learning journey. In this video, let's build the model and perform the fit on our dataset. Now to build the model, I'm just going to build my model as a sequential model. But again, hey guys, you're free to use functional API, or you can also create your own model as a class as well with the help of subclassing API. Now if you're new to these concepts, you can check out our other videos where we have explained about the various ways of creating the neural networks from scratch. Alright. So let's start building. I'm going to say that model is equal to tf tensorflow dot keras dot models dot sequential. Okay, now once I build this model as sequential, I'm just going to add the various layers. Let's do one thing. I'll take care of imports at the start itself so that I can just mention my only layers over here, guys. Okay, so here in the imports, import tensorflow as tf. All right, and from tensorflow dot keras dot models import sequential, and this is followed by I'll also import the individual layers as well. From tensorflow dot keras dot layers, from the layers I want to import input layer, Conv2D layer, and then I'll import my flattening layer, dense layer, and I'll also import dropout layer as well if I want to use it at a later point. And let me just use this maxpool2D as well. Okay, so these are the various layers that I can use, and I'll also import some data pre-processing from my keras. So I'll say from tensorflow dot keras dot pre-processing dot image import load img comma img to array. Okay, so this will take care of necessary imports, and now we can start building the model without worrying, guys. Okay, so I'll say model is equal to sequential, and after defining my model as a sequential model, I can just go ahead and add the various layers. So I'll say model dot add conv2D. all right, and the filters is, let's assume I'll have the 16 filters over here, and I'm going to specify my kernel size to be equal to 3,3, and I'll use my activation is equal to relu. And once the activation is specified, this is followed up by input shape, because this is my first layer. So input shape is equal to 224, 224, 3. Okay, so this is going to add our first convolution layer. Now, one thing that you always have to notice, when we are working with convolution layers, we don't have to perform the flattening operation. We will send the image data as it is when we are sending it to the convolution layer. But if I'm sending the data for my dense layer, in such scenarios, I'll have to do the flattening operation. Now in this scenario, this is a convolution layer, hence I'm just specifying my input shape as it is 224, 224, 3. And in this first layer, there are 16 filters, and each filter is of the shape 3, 3, and the activation of such filters is relu activation function. Now I'm going to add my second layer, and for the second layer, I'll also have another convolution layers, and this will have some 32 filters. Okay, and the activation, let it be relu itself, and I'll use the same kernel size, so I don't have to specify my input shape because that will be determined from my previous layer. And once these two convolution operations are complete, I'm going to perform pooling operation. So I'm going to say it as model.add maxpool2D. So I'm applying the max pooling operation on the output that I'm getting from my convolution layer, and I'll specify my pool size is equal to 2, 2. Okay, once this is done, I'm just going to again perform another convolutional operation followed by max pooling. So this time I'll have 62 filters and I'll use the same kernel size of 3,3 with the relay activation function followed by a max pool 2D layer, and I'll have one more layer of convolution layer which has 128 filters and activation as ReLU. Now once this is complete, the next thing will be is once the series of convolution operations are complete, I'll be connecting to a dense neural network. Now to connect it to a dense layer, I have to make sure that I'm performing the flattening operation. So I'm going to say it as model.add flatten. So this will take care of flattening operation. And then I'm going to convert this flattened output into a dense layer. So dense, and I'll have, let's assume 64 neurons, and I'll use the activation as ReLU. And this is followed up by, let me add a last neuron. Okay, so since this is a simple binary classification, I'll say model.add dense1 activation is equal to sigmoid. And once this is done, I'm just going to display the model summary. Okay, so this is how the model would look like. So my input is of the shape 224, 224, 3. Now as a result of applying my first convolution layer, the shapes have been transformed and the resulting shape is 222, 222, 16. That means I have lost a dimension along each axis, which means that I am losing the dimension because of performing this convolution layer, because I'm not using any padding. And the third dimension has been changed to be 16. This is because there are 16 filters. In the next layer, we have 32 filters. And after this second convolution layer, this is followed up by max pooling layer. See, when I perform this max pooling operation, I have reduced the size by half. This is followed up by another convolution layer, then followed up by max pooling layer, convolution, max pooling. So here the output of max pooling is being sent to flattening layer. Now by sending to flattening layer, I'll be actually converting it to a single dimensional vector. And this flattened input is sent to my dense layer. And in my output layer, I'm having a single neuron with sigmoid activation function because I'm performing the task of binary classification. Alright, now once this is complete, I'll go ahead and compile the model. Now to compile the model, I just have to specify my loss function, optimizer, and the metrics. So model.compile loss is equal to tf.krs.binary cross entropy alright, and I'm going to use my optimizer as Adam. Now you're free to use any optimizer, guys, but this is what I'll be using, which I found to be performing well compared to others. So metrics is accuracy. Okay, now this is going to perform the compile operation. Now this is followed by performing the fit. Okay, now before we perform the fit, we also have the option to specify our model checkpoint. So let's add the same thing, guys. I'm going to import my keras callback. I'm going to say it as from tensorflow.keras.callbacks. I'm going to import model checkpoint as well as early stopping. Now I'm going to define how the early stopping and the model checkpoint should work. Hey guys, if you're new to this, please check out our other videos as how to make use of keras callbacks. So I'm going to specify it as early stopping, and inside the parenthesis I want to monitor my validation accuracy. Okay, and I'm going to say it as minimum delta is equal to 0.01 and patience is equal to 5, verbose is equal to 1. Now this means that monitor my validation accuracy, okay, and wait for 5 epochs. If the improvement doesn't, if there is no improvement in validation accuracy even after 5 epochs, just stop the training. Okay, so that is what my keyless callback is specifying over here. Now along with this, I'm also going to create my model checkpoint. So I'll say it as model checkpoint is equal to model checkpoint, and here I'm going to specify my model. Okay, my best model.h5, and I want to monitor the same validation accuracy, and then I want to say it as save best only true, because I want to save the best models only. Okay, and along with this, I'll also specify verbose is equal to 1, because I want to display what is happening over there. Alright, so this is going to take care of creation of model callbacks. Now I'll use these callbacks when I'm performing the fit. So I'll say history is equal to model.fit, and inside the parenthesis it's train data followed by validation data is equal to val data. Alright, I'm going to reduce the number of validation steps, because I'll say validation steps is equal to 16. Okay, steps per epoch is equal to 16. Okay, I'll say epochs is equal to 30, verbose is equal to 1, and for the callbacks, this is consist of my early stopping and model checkpoint. Okay, now observe closely here. I'm using a different terminologies over here. So model.fit, I'm specifying my training data. Now if you observe, this training data is nothing but the data that I have created earlier, which flows from directory. Okay, this you are at least a straightforward one, and this is a validation data. Now along with these two, there's an additional argument that I have used, that is called as validation steps and steps per epoch. Now let me do one thing. Let me just execute this cell. Let it start executing in the backend, and then I'm going to explain about these two steps. Okay. Okay. So the training of my model has been started. Now here I have mentioned my validation steps is equal to 16. So, and also if you remember, I have specified my batch size to be equal to 32. Now if you remember, what happens when there is an update? So whenever there is an update, it loads 32 images, and after it loads this 32 images, it is going to update my parameters. Okay, so after loading the batch size of 32 images, it is going to update the parameters of my deep learning model. Now observe what am I specifying over here. I'm saying it as steps per epoch is equal to 16, which means load 32 images 16 times. Okay, and once you load the 32 images 16 times, and once you update it 16 times, count it as a 1 epoch. Okay, and likewise do it for 30 epochs. So that is what this steps per epoch would mean. So if I have 100, or let's assume 6,000 images, from this 1000 images, each time I'm going to load 32 images, and I load this 32 images. Using this 32 images, I'm going to do the update on my parameters, and after this thing, I'm going to obviously load another 32 images. Now here I've done the update once, then I'll load the 32 images and I'll do the second update. Likewise, I'm telling my system as do 16 updates to count it as 1 epoch. Now if I don't specify this as do it as 16 steps, it is going to load as many number of images that I'm having. Now let's assume in my training data I'm having 4000 images. Then if I want to count it to be as 1 epoch, I'll have to process all these 4000 images. But instead I'm saying it as just load 32 into 16 images for each epoch. So that is what I'm telling for my system. The reason that I'm taking this approach, because as you know, there is lots of data over here with me. and I don't want to wait for too long. Hence, I have used this concept. I've just simply mentioned as steps per epoch as 16, and you are free to remove this parameter and train it on your entire data set. All right. So let's see the training progress. See, it's still getting trained, guys. It's still taking a lot of time to train. So what I'll do is I'll let it train like this, and I'll see you in the next video where we explore more about how the training is performing and what we can do to improve this training. So I'll see you in the next video, guys.